Good day to you all, and thank you for taking the time to listen to this presentation. My name is Dr. Michael Farnsworth. I'm a researcher along with many others in the FEMM Hub, and I'm focused upon research within the grand challenge theme of in-process tracking and traceability for electrical machine manufacture. So this is part A of this particular talk, and you can find part B in another delivered by our colleague, Dr. Divya Tiwari. So let's begin. So electrical machine or motor manufacture is a really fascinating area of industry and research, and it's certainly been growing over the last decade. As you can see here, it involves many kinds of activities and tasks, from physical processes such as stamping and welding to assembly tasks such as connections and terminations. Now, what we were interested in can broadly be defined as the digitization of these EM manufacturing processes, and then to gain some value out of this, be it in-process monitoring or quality control, or perhaps simply to aid operators in a specific manual task. We define this digitization work as a whole around in-process tracking and traceability of EM manufacture, with a focus on three key main areas. The first, naturally, is the sensorization, for lack of a better word, of the key processes we are interested in. Now, we at first can't explore every activity or task in electrical machine manufacture, so we have chosen to focus on those activities which can be easily digitized and also contain some degree of manual activity. In this case, our focus recently has been on coil windings, cables, connections and terminations. The second focus is on modeling and simulation of electrical machine manufacturing processes, and how we can determine if any interdependencies between activities have downstream effects on performance or quality. Divya will explore this more in our talk in part B. Finally, in relation to manual activities, we are interested in whether it's possible to digitize and track the processes that occur in conjunction with the second step, and gain enough understanding to remove the need for certain tests that occur at the end of the electrical machine manufacturing process. So where do we begin? Well, one of the challenges in the life cycle of electrical machines is naturally the loss of function, often a result of some form of failure, in this case, coils and windings. Here we can see two such examples: a grounded wire or a winding short circuit, often the result of high temperature due to a short circuit or contacting, often where insulation failure has occurred, but also possible as a result of the coil geometry. So our first task was therefore to investigate whether we could characterize wound coils using available state-of-the-art machine vision techniques. Though there are a number of possible characteristics to choose from, insulation deterioration for example, we chose to go with a more structural failure in the wound coils. Shown on the right, specific kinds of winding failure, such as the crossover wires or gaps, are undesirable and need to be identified during the process. So what we set out to do was essentially 3D print some stator segments and build a suitable test rig to begin experimentation. We then used this test rig to create a database of coil images, exhibiting three kinds of state. In this case, a good coil, i.e. pass, or a failed coil, i.e. gap or crossover. This database included variations in zoom and lighting and angle to provide as many examples as possible. And we can see more detail here what was captured. Here is a coil on the left, which is characterized as pass. It is hand wound, so it's not perfect, but for our purposes it's good enough. And on the right we have one with a wire crossing fault. With our images in hand, the next step is to build a model capable of characterizing these kinds of failures on its own. For this we turn to deep neural networks, particularly the class of convolutional neural networks so common in many machine vision systems. Taking a state-of-the-art model, called ResNet, we retrained through a technique called transfer learning on our new image dataset. One of the challenges we had is the limited number of images and the fact it was quite unbalanced. Though it is possible to create many examples for a gap and crossover, essentially unwinding it a bit and moving the gap crossover segment up the coil to create a new image, this is not possible for the past examples. We have to start from anew. At any rate, we trained this model using three different approaches. The first with the original dataset, the second with additional processing of the images, and finally, and I will discuss this in more detail later, a GAN-generated dataset. So what we were able to show was that you can learn a model, even with such a small dataset, to accurately characterize individual coils. There was a clear advantage to performing the processing. In this case, the graphical algorithm to isolate the coil and additional color shift, while the original dataset models have lower performance, though still very capable. However, they were a little unbalanced, as we discussed before, when it comes to false positives and negatives, as I shall show in a second. But before we do that, let me first jump back and give a brief overview of what GANs are and the motivation to use them. Within manufacturing, particularly where failure occurs, such as our coil winding failure examples, the data or images is limited. We often lack enough examples to train DNN type models we wish to use. This is a challenge for many deep neural network models and a recent focus in research. With work in what is often called few-shot or one-shot learning, basically training models on very limited data, currently highly in vogue. However, one alternative to this, and one I find particularly fascinating, are the area of generative models. In this case, generative adversarial networks, i.e. GANs. This is best described as a model which learns the data distribution of the examples you train it on, so as to be capable of generating new examples of data from this learned model. Here you can see, once again through a transfer learning approach on a GAN called style GAN, we are able to generate new images of butterflies from a previous data set it was trained on. Now you can see in the middle here the transversing of the latent space, so we can move through this model's latent space and explore the different types of butterfly images that can be generated. So what we can do is repeat this process, but using our coil image dataset instead to create our coil generating model. You can see how it learns over time and generates reasonably accurate examples. On the left, we have the model being trained over time and its accuracy and its ability to generate new coils. In the middle, we can see once again transversing the latent space, and on the right, we can see examples that were created. Therefore, this allows us to simply boost our unbalanced dataset with new images in the hope of improving the classification accuracy of the model. On the right, you can see some crossover examples, and though not perfect, hopefully they are representative enough of the particular failure class to allow the model to differentiate between the different classes that exist. So what were the results of this approach? Well, if we go back several slides, we saw that both the original and GAN approaches achieved around 60 to 75%, 70% accuracy, with the GAN model around 3 to 4% boost in performance over the original. One of the big differences, however, lies in the precision and recall of the two models. The original model learned to more or less classify all gap images as pass. However, by boosting the unbalanced dataset, this bias was mitigated. And this is obviously mitigated further using the processed image dataset. Now, ideally, further improvements could be made to this GAN approach, in particular further training and higher resolution image generation. We didn't train it for very long, given the limited resources at the time. I think further training would improve this particular approach and hopefully bring it more in line with what we see with the processed imaging example. But it has shown potential. So that was a brief overview of one part of our research. So let's now look at another, in-process tracking and traceability of manual activities. When it comes to coils, wires, cables and terminations, depending on the kind of electric motor, the amount of manual intervention varies. However, we go with the assumption that these activities do and will involve human operator interaction. So the research we're interested in, therefore, is how can we digitize, for the purpose of tracking traceability, these activities, with the aim to help or allow in real time anomaly detection, guidance, or some form of process monitoring. So what we have sought to do is break down this task into sort of three main steps or goals. The first is object detection. So can we identify from a scene or image the objects of interest, for example the hands and cables or wires present. The second is to go further and see if we can segment out the actual object of interest from the scene for further processing or value as shown with the motorcycle image. Finally, with this 2D image, is it possible to build a 3D model that we can record and track over time to allow us to do those things mentioned previously? So, firstly, we built an entire new dataset of images and videos from a number of coil winding and cable manipulation activities or scenarios using our test kit demonstrator. This dataset consists of a number of unique experiments, sensor modalities, and scenarios. So beginning with our first attempt at cable segmentation, so trying to identify in a scene and extract from a scene a cable, we took a more engineered approach. So there's a technique called Ariande, and it was developed by researchers elsewhere. And the approach takes an image, and what it looks to do is convert it into a number of what are called superpixels, as you can see on the right. So these are pixels that are grouped together in terms of color or texture. The algorithm treats each superpixel as a sort of node in a graph and tries to connect all the superpixels into a single string that ideally represents the cable of interest. This approach worked reasonably well, as you can see in the video below, providing capabilities for tracking cable position. However, it is quite slow and can't really run in real time. It also requires sort of knowledge of the start and end positions of the cable. So therefore, it's useful in sort of demonstrating a more engineered approach, but when it comes to real-time in-process tracking and traceability, it has its limitations. As a result, we then look to try out a more end-to-end approach, using, once again, deep neural networks. In this case, a U-Net architecture. So this model is designed for what's called pixel-level segmentation. Essentially, it learns to classify individual pixels, as seen with the bike and rider in the top. It performs well on the small data set it is trained on, as seen with the prediction in the bottom. Bright values are higher pixel level prediction probabilities, so essentially trying to determine whether that particular pixel is a cable or not. And we can see over time it trains reasonably well to actually predict in this data set what is a cable and what isn't. However, we apply it to our cable manipulation example, so the videos and images data set we had before, and the results were mixed. So it is certainly capable of segmenting out the cable. However, there are sort of significant false positives, often related, as you can see, to certain edges and lighting conditions in the particular image. And this is obviously not ideal. So for now, let's leave segmentation and move on to something else. We'll come back to segmentation in a bit. Let's jump to a new challenge, something called object detection, particularly in real time. So once again, here deep neural networks dominate. And there exist many examples, as seen on the right, of successful applications. In this case, tracking cars. And on the bottom right, more applicable to our work, tracking hands. Below is a specific use case called ego hands. So this is a data set based upon an egocentric view of hands and their detection. So what we tried next was to train a number of these models available, so YOLO, MobileNet, SSD, and see how well they performed on our data set, our examples. So once again, the results were mixed, though not too bad. The generalization abilities of the model means it was somewhat capable of performing hand detection, probably at around 70%, but it's far from perfect. There are sort of dropouts in terms of identifying where the position of the hand is, and in these particular video examples that we have, we can see as you get close to the camera, it drops out. So one of the reasons is simply that our use case is perhaps too outside of the training data used to build the model. So too outside that ego hands data set. So to alleviate this, we went about creating our own object detection and segmentation data set, using a well-known annotator in what was and still is a tedious task, but oh well, that's life. We then used this to train a state-of-the-art model called YOLO-ACT, and the end results were certainly more impressive, with real-time object detection and segmentation of both the cable and hands in an image or scene. There are drop frames, as before, somewhat due to limited training data set. So the data set we created with the annotator was about 350 images, so it's very small, comparative to the tens of thousands that you ideally want in a particular scenario. But we hopefully can create more later on. So that's the end of this talk. Thank you for holding on and sticking with it. I was just sort of a brief overview of some of the research we're doing currently at the moment. I just want to end on our sort of future outlook. A lot of this work and the data sets generated are open source and held on our repository, which we plan to open source soon. Another thread of research, the digitization of coil winding processes, particularly from the spool, is now ongoing. We have a small lab-based winder, you can see in the top right. We hope to get some interesting data and results from that. We're also investigating some interesting sensing modalities, such as this event-based camera approach for high-speed coil winding. Though perhaps the video clip I use is a bit misleading because this is done by hand, it does show what the event-based camera data looks like. So rather than an RGB or RGB depth type camera capturing frames over a typical time period, an event-based camera captures per pixel changes in brightness at very high speeds and resolutions. Also, the work to sort of transform our 2D object segmentations, so that would be the cables and hands, to 3D models is also ongoing, with some exciting models available to use out there in the wild. So with that, I shall end with a thank you, and a reminder to please look into part B of this talk with Dr. Divya Tiwari and her work on modeling of interdependencies and Litz wire termination processes. That's all from me, and thank you very much.